As you know, a power plant uses energy to produce energy. The whole purpose of your plant is to take energy from fuel and convert it into electrical energy. But the process of converting energy from one form to another also takes place in many of the components that enable your plant to fulfill its purpose. In this unit, we're going to look at 3 of these components. First, we'll see how your plant's batteries convert chemical energy into electrical energy and vice versa. And then we'll see how AC and DC generators convert mechanical energy into electrical energy. Finally, we'll look at motors. Motors work just the opposite from generators. They convert electrical energy into the mechanical energy that's needed to keep most of your plant's equipment running. Okay then, let's start with batteries. If your plant has had a loss of AC power since you've been there, you can appreciate what the plant's batteries do. Batteries supply emergency power for lights, for controls, for DC lube oil pumps, and for some vital motors. Batteries take over when other power is lost. With battery power, you don't have to stumble around in the dark. You can keep critical equipment running, and you can keep the turbine generators lubricated as they coast down to a stop. In addition to functioning as an emergency power source, plant batteries also supply power all the time to many of the plant's control systems. Relays, circuit breakers, and indicating lights may all depend on battery power. If the plant loses its main AC power supply, you need indicators to tell you what's on, what's off, and what's happening in various parts of the plant. Without that control panel indication to tell you exactly what is happening, you might not know which situation to handle first. If you do the wrong thing, you could run the risk of injuring personnel or damaging millions of dollars worth of equipment. Because you don't know when you're going to need the emergency power that plant batteries can provide, you have to make sure that they're always ready for action. This means understanding how they work and making sure they get the attention they need. Before we go into the specifics of a big plant battery, let's back up a minute and review some of the basic facts that you already know about batteries. Back in Unit 1, we talked about how batteries use chemical action to produce voltage. We said that all batteries are made up of cells. One cell, like a flashlight battery, or perhaps 60 or 120 cells, like some plant batteries. We went on to say that each cell consists of 2 electrodes, which are usually plates made of different materials, and a solution called an electrolyte, which is usually a paste or a liquid. We talked about 2 types of cells, primary cells and secondary cells. We said that a primary cell can't be recharged after its energy has been used up, but a secondary cell can. We also said that we'd talk more about batteries later. Well, the facts I gave you about batteries in Unit 1 are true, but there's more to batteries than what we covered earlier. For instance, I can add a bit more information to what we've said about the difference between primary and secondary cells. Both types of cells convert chemical energy to electrical energy. The difference is that a primary cell makes this conversion directly and a secondary cell doesn't. What I mean is that a primary cell uses the chemical materials within the cell to start the chemical action needed to make the conversion. It doesn't need any outside help. A secondary cell, on the other hand, has to have energy added to it before it can convert chemical energy to electrical energy. A secondary cell is often called a storage cell because it stores the energy that's added to it and then uses that energy when it's called on to produce voltage. Another difference between a primary cell and a secondary cell is that a secondary cell can be recharged and reused again and again, while a primary cell can't. Now, your car's battery is made up of secondary cells. If it dies, you get it charged, and off you go. A flashlight battery is a primary cell. When it dies, you throw it out. Your plant's batteries are composed of secondary cells. So let's look at how this type of battery is constructed, how it works, and how it gets the energy it needs to operate. We said earlier that a battery can be made up of one cell or many cells. In a large plant battery, there are a lot of cells. all connected in series with each other. As you know, in a series connection, we add the voltages produced by each cell to get the total voltage produced by the battery. So, for example, if this battery contains 60 cells, and each cell produces 2.2 volts when it's fully charged, the total amount of voltage produced by this battery is 60 times 2.2, or 132 volts. Some plants have a 132 volt DC battery for control and indication, and a 260 volt DC battery for large DC motors and other components. This larger battery would require 120 cells. You should also be aware that the battery or batteries in your plant may not produce a voltage of 2.2 volts per cell. Other typical values include 2.15 and 2.212 volts per cell. All of the cells in a particular battery are identical, so we can examine one cell to see how they all work. Here, you can see the parts of a typical secondary cell. These two groups of plates are the electrodes. One electrode is positive and the other is negative. Each electrode is made up of a group of plates rather than a single plate to increase the surface area of the electrode. Increasing the surface area increases the efficiency of the chemical action that occurs in the cell. The result is that the cell's voltage output is extended for a longer time. Notice that the plates of the positive electrode and the plates of the negative electrode alternate. First a positive plate, then a negative plate, then another positive plate, and so on. This arrangement improves the efficiency of the cell by cutting down the cell's internal electrical resistance. The closer together the plates are, the less resistance there is. The thin sheets between the plates are separators. They're made of non-conducting porous materials, and their purpose is to keep the plates from touching each other and shorting. All the plates for each electrode are connected by a lead strap. The strap connects to the positive or negative terminal. The terminals are the points where each cell in your plant's battery is connected to the cells on either side of it. The electrolyte in this cell contains acid, so the internal parts of the cell are sealed in a container that is acid resistant. There's a filler plug at the top of the container. You can remove the filler plug if you want to take a sample of the electrolyte to test its composition, if you want to check the temperature of the electrolyte, or if you need to add water to the cell. Most filler plugs, like this one, have a vent hole to allow gases formed during chemical action to escape from the cell. Okay, that's what a typical secondary cell looks like. Now, let's see how it works. We said earlier that a secondary cell has to have energy added to it before it can do anything. Adding energy to a secondary cell is called charging the cell. Only a charged secondary cell can convert chemical energy into electrical energy. Let's start by assuming that this secondary cell has never been charged. This particular cell is a lead-acid cell, one of the most commonly used types of storage cells. Both of the electrodes are made of lead sulfate, and the electrolyte is mostly distilled water, with only a very small amount of sulfuric acid mixed in. We said earlier that a battery needs electrodes made of different materials, but this cell has two electrodes made of lead sulfate. Now, these electrodes have many plates. As long as the cell is uncharged and has two electrodes made of the same material, it cannot produce voltage. However, when an electrical charge is applied to the cell, things start to change. One lead sulfate electrode changes into sponge lead, and the other one changes into lead peroxide. Now, we have electrodes made of two different materials. The electrolyte, which was mostly distilled water, becomes mostly sulfuric acid, a solution that is chemically active. When these conditions exist, the cell is charged. As this other cell is being charged, the water in it breaks down, and two gases are given off, hydrogen and oxygen. The gases bubble up through the electrolyte as the water changes to sulfuric acid, and they escape from the cell through vent holes like the one we saw earlier. The escaping hydrogen gas can be extremely dangerous as it mixes with air. As little as 8% hydrogen in the air can be an explosive mixture. Also, as more hydrogen and oxygen leave the cell in the form of gases, there is less water left in the cell. If the water level gets low, more distilled water must be added to the cell to keep the electrodes from becoming hard and brittle and to continue the chemical reaction. Okay, now suppose this cell is charged and ready for action. At its peak, this cell can produce about 2.2 volts. But as it discharges, that is, as a circuit uses the voltage that the cell produces, the voltage decreases. Eventually, it drops below a useful level, as we'll see in a little while. As a lead-acid cell discharges, the chemical action that takes place is just the reverse of what we saw while the cell was being charged. During discharge, the sponge lead electrode and the lead peroxide electrode both change back into lead sulfate, and the electrolyte changes from mostly sulfuric acid to mostly water. Discharging the cell puts us back where we started from. We've come full circle. If we want this cell to produce voltage again, we have to give it another charge. Then the whole process starts all over. In the next segment, we'll see how a secondary battery gets the charge that makes it work. We'll also cover battery maintenance and safety precautions. Before we go on, though, read through the material in your text on how a secondary cell changes chemical energy into electrical energy and vice versa. If you have any questions, ask your instructor. As a general rule, storage batteries are kept charged. One reason for this is obvious. When you think about your plant's battery or the battery in your car, if they aren't charged, they can't supply power when you need it. And the other major reason for keeping a lead-acid cell charged is that the electrodes become hard and brittle if the cell is even partially discharged for a long period of time. Hard and brittle electrodes won't react properly with the electrolyte, and the battery won't be able to do its job. Now, before we get into how batteries are charged, there's one more thing you should know about discharged batteries. Even when a storage battery is completely discharged, it still shows a voltage when it's tested. The voltage is very low, however, and it won't give you much in the way of current flow. This battery is an automotive type, 12-volt battery. It has 6 cells, and when the battery is fully charged, each cell produces 2.2 volts. The cells in the battery are connected in series, so the total output of the battery is 6 times 2.2, or 13.2 volts. Now, this battery is completely discharged, so it won't produce 13.2 volts. I'll use a voltmeter to see just how much voltage it can put out. Most storage batteries have a discharge value of about 1.7 volts per cell. Now, if this battery is like most, then I should get a reading of a little more than 10 volts. 1.7 times the 6 cells in the battery comes out to just over 10. All right, positive to positive, negative to negative. The voltmeter shows a little more than 10 volts. The difference between 13.2 volts from a fully charged battery and 10 volts from a completely discharged one doesn't sound very significant. Well, let me show you the difference. I'll use 2 batteries, one fully charged, one fully discharged. First, I'll put the fully charged battery into this circuit. And having done that, I'll close the switch. We see what happens. Well, light bulb came on right away, didn't it? Bright. Okay. Now I'll remove this battery from the circuit and put in one that's discharged. And we should be able to see a difference. When I connect up this battery and close the switch, light comes on very slowly and is very dim. There is a difference, isn't there? The discharged battery does produce some voltage, but not enough to do any useful work. Okay, since we know that a battery isn't much good unless it's charged, the next logical question is, what do we do to charge a battery? What do we use? Well, the most common type of battery charger is a constant voltage charger like this one. When you use a constant voltage charger, you set the charger to the normal operating voltage of the battery you're hooking it to. The charger will then keep the battery charged to that voltage, and you won't have to worry about accidental overcharging. This meter on the charger shows you the amount of current in amps that the charger is putting out. In most plants, the battery charger also supplies current to some control and indicating systems that are connected in parallel with the battery. If the plant loses AC power, the battery charger stops working, but the control and indicating systems continue to operate on power supplied by the battery. So the amp reading on the charger meter shows the amount of current being supplied to the control and indicating systems as well as to the battery. The battery charger keeps the battery supplied with the amount of current it needs. For example, if the battery is completely discharged, the charger will supply it with a large amount of current. The charger provides smaller amounts of current as the battery's needs decrease. When the battery is fully charged, almost no current is needed, so if the amp reading on the meter is a high number, the battery is discharged and the charger is recharging it. The lower the amp reading, the closer the battery is to being fully charged. Looking at the amount of current flowing into the battery gives you an indication of the state of charge of the battery as a whole, but not the state of charge of each cell. One cell might be unable to take a charge for some reason, even though all the other cells are fully charged. To find out the state of charge of each cell, you should measure the voltage of each cell, or you could measure the specific gravity of the electrolyte in each cell. Specific gravity is the ratio of the density of a substance to the density of water. So when we measure the specific gravity of the electrolyte in a cell, we can find out how much acid it contains. Acid is denser than water, so if we get a high specific gravity reading, we know we have a lot of acid. A low reading means a much smaller amount of acid. As you know, when a cell is fully charged, there's a lot of acid in the electrolyte. When the cell is discharged, the electrolyte is mostly water with very little acid. So if we find out how much acid a cell contains, we'll know its state of charge. Specific gravity is usually measured with a hydrometer, like this one. As you can see, it looks like a syringe. A sample of the electrolyte being tested is drawn up into this glass barrel. There's a float inside the barrel. The float is weighted at one end to keep it upright. The scale on the float typically reads from about 1.110 to about 1.300. We'll see why in a minute. You can see how specific gravity testing is done here. Notice the protective equipment. Anyone who makes a specific gravity test or does any other work on or around a battery should wear equipment that provides protection from contact with acid. The test is begun by discharging the air from the hydrometer and then putting the bottom part of the hydrometer into the cell. Atmospheric pressure will push a sample of the electrolyte up into the hydrometer. When you use a hydrometer, be careful not to draw in too much liquid. If you do, the float may hit the top of the tube and you'll get a false reading. Now, this tube doesn't have too much liquid in it. As you can see, the float sinks to a certain level inside the barrel. The level of the float indicates the specific gravity of the electrolyte. If the cell is discharged, the scale on the float will read between 1.110 and 1.130 for most lead-acid batteries. If the cell is charged, the scale will probably read between 1.260 and 1.280. The reading on each cell tested is written down. The number of readings taken usually depends on plant policy. Sometimes cells are checked at random. Sometimes specific cells are checked. And sometimes all the cells are checked at periodic intervals. After the specific gravity readings are recorded, they may have to be corrected to allow for variations in temperature. Changing the temperature of a substance changes its specific gravity. The specific gravity of sulfuric acid, for example, is different at different temperatures. A thermometer can be inserted into a cell to check its temperature when specific gravity testing is being done. The method used to correct for temperature variations isn't the same for all batteries. Be sure to check the battery manufacturer's information manual if you're going to be working with specific gravity readings. Okay, now that we've seen how to tell how much charge a battery has, let's look at how we can tell how long a battery should last before it's discharged. If you lose AC power in your plant, it's important for you to know how long your battery will last without the battery charger before it leaves you in the dark. Batteries are rated according to the amount of current they can supply for a given amount of time. The rating is usually given in ampere hours. For many storage batteries, the hours part of ampere hours is assumed to be 20 hours. So, if such a storage battery is rated at 100 ampere hours, it can supply 5 amperes for 20 hours before the voltage drops to the discharge level of about 1.7 volts per cell. As we saw earlier, with 1.7 volts per cell, a battery can't perform any useful work. A battery can also supply more current for less time or less current for more time with the same ampere hours rating. For example, a battery rated at 100 ampere hours can supply 50 amperes for 2 hours or 4 amperes for 25 hours. So if you want to find out how long a battery will last, you can just divide the rate of discharge in amps into the ampere hours rating. Finally, we come to the part about batteries that I hope you'll remember best. I'm talking about the safety precautions associated with handling or working around batteries. I said earlier that hydrogen gas is released from a battery as chemical action takes place, and that this gas can be an explosion hazard. For this reason, you must not smoke around batteries. Also, make sure that there are no open flames or sparks in the area. They could set off an explosion. To reduce the chance of an explosion, adequate ventilation is essential in a battery room. With proper ventilation, hydrogen gas can get out of the room before it builds up to a dangerous level. Whenever you're working around a battery, be sure to wear eye protection and any other protective gear that your plant requires for protection from acid. Things like masks, rubber aprons, and rubber sleeves should protect you from acid spills and splashes. But you should know what to do in case they don't. Make sure you know where the closest eye wash station and shower are before you enter a battery room. If you get acid in your eyes or on your skin, the first thing to do is wash the area with large amounts of water. Then get help. If you get acid on your clothes, it'll probably cause holes, but you can minimize the damage by neutralizing the acid. Use dilute ammonia or a solution of baking soda and water. Now, one final precaution. A battery cell will short whenever a piece of metal touches both of its terminals. Shorting the battery in this way can cause a tremendous amount of current to flow, with resulting personal injury and serious equipment damage. So be very careful with metal around a battery. Make sure that you use tools that will not accidentally cause a short. For example, a long metal screwdriver would be a poor choice because it could touch both terminals. Well, we've covered a lot of information in this segment. We talked about how a secondary battery is charged and how it's rated. We also examined some of the hazards that it presents, and we learned how to protect ourselves from these hazards. Why don't you take some time now to read over the material in segment 2 of your text and make sure it's all clear to you. If you have any questions, discuss them with your instructor before we go on. For the rest of this unit, we're going to talk about 2 of your plant's most important components, generators and motors. We've covered most of the fundamentals in previous units. Now you'll start to see how everything fits together. Can you imagine what would happen if all your generators failed? In fact, if all the generators in the system failed at once and no one could get them back online, there'd be no power and everything would stop. Businesses, hospitals, traffic signals, all at a standstill. Oh, there'd be emergency power available from some batteries for a while, but when that ran out, we'd be back to candlelight and fireside chats, and the world as we know it would cease to function. The word blackout used to mean lights out during bombing raids in Europe. On the East Coast a while back, it meant total chaos. We got a taste of how important electricity was then, even if it had never occurred to us before. Well, an operator can go a long way in keeping electricity available by understanding how a generator works, being able to spot a problem before it becomes serious, and dealing with it effectively. As an operator, you're one of the most important people in the plant. What we're going to talk about in this segment are the fundamentals of how an AC generator works. First, a single-phase generator, and then a three-phase generator. We're going to cover exactly how these generators convert mechanical energy into electrical energy. When we talked about alternating current in Unit 2, we saw how a simple AC generator produced a voltage. We saw that voltage used to light up a bulb. We saw how the output of an AC generator could be plotted. We'll review all that, and we'll go on to introduce some new terms. Finally, we'll look at how a three-phase generator works. Two important things you'll learn about generators are how the output voltage and the frequency are controlled. You don't have to alter the generator's frequency much, except when you're putting it online. But when you do it, you have to do it right. All generators work just about the same way. They produce electricity by rotating a group of conductors through a magnetic field, or by rotating a magnetic field in a group of conductors. The energy input to a generator is the mechanical energy needed to rotate the moving parts. This energy can be supplied by gasoline or diesel engines, by electric motors, by flowing water, or by steam turbines like the one in your plant. Anything that can make a shaft rotate can be the input to an electrical generator. The output of a generator is the electrical energy it produces. Since all generators require a magnetic field to operate, you could say that a generator is a device that converts mechanical energy into electrical energy by means of a magnetic field or by magnetic induction. So let's get right down to how magnetic induction produces voltage. As you know, you need three things to get an induced voltage: a conductor, a magnetic field, and relative motion. In a generator, the motion part is provided by mechanical energy. There's a direct relationship between the amount of mechanical energy that goes into a generator and the amount of voltage that comes out. In fact, if you change any of the three things on our list, the conductor, the magnetic field, or the mechanical input, then the amount of voltage also changes. Now, here's the simple AC generator we saw in Unit 2. As the generator turns, voltage and current build up to a peak positive value and then decrease to zero. At this point, current and voltage reverse direction and build up to a peak negative value. Then they decrease to zero and the cycle is complete. During each cycle, the current flowing through the bulb causes it to brighten, dim, go out, brighten, dim, and go out again. This cycle is repeated 60 times per second in a typical power system. Well, that's about all we need to review on this simple generator. It's classified as a single-phase generator. The next generator we're going to look at is also a single-phase generator, but its operation is a bit different. This generator uses an electromagnet instead of a permanent magnet. And the magnetic field rotates, not the conductor. Because the magnetic field, or just field as it's commonly called, rotates, it's called the rotor. The rotor is always the part of a generator that rotates. The part that stays still is called the stator. In this generator, the stator is also the armature, which means that it's the part where the voltage is generated, or induced. The rotor in this generator completes a cycle each time both a north pole and a south pole pass the winding. Remember, in this generator, the field rotates, not the conductor. Each time the north pole of the field passes the winding, the peak positive voltage is induced. As the south pole passes the winding, the peak negative voltage is induced. Voltage is induced in the winding, and from there, current moves on into a circuit. The speed of the rotor in this generator determines the number of cycles it completes each second. A complete revolution of the rotor every second means a complete cycle every second, because both the north pole and the south pole of the rotor pass the winding during that time. Now, when you're talking about the number of cycles per second, you're talking about frequency. Frequency is measured in cycles per second, or hertz, remember? Most generators in the United States operate at a frequency of 60 hertz, but not all generators are built like this one. This generator has two poles, one north pole and one south pole. Some other generators have more poles, with different numbers of poles. The rotors turn at different speeds. Think of it this way. The rotor on a 4-pole generator only needs to make 1/2 of a revolution to complete a cycle. Only one north pole and one south pole need to pass the winding to make one complete cycle. If the rotor in a 4-pole generator makes a complete revolution in 1 second, it will produce 2 hertz. If you look at the generators in the plant, you'll notice that they're all producing 60 hertz, but they may not all be turning at the same speed. This is because they may not all have the same number of poles. As an operator, you'll have to adjust the frequency of your generators to 60 hertz when you're putting them online. To do this, you'll have to know each generator's proper operating speed. There's a formula you can use that relates the frequency of a generator to its operating speed and to the number of poles it has. It goes like this. F equals RPM times the number of poles over 120. What that is now is frequency equals revolutions per minute times the number of poles divided by 120. Let's assume that we want to set a 2-pole generator at 60 hertz. First, we put the numbers we know into the formula. 60 hertz equals RPM times 2 divided by 120. And then we solve for RPM. Multiply both sides by 120. You get 7,200 hertz equals RPM times 2. Then divide both sides by 2, and the answer is 3,600 RPM. To set this generator at 60 hertz, you adjust the speed of the rotor to 3,600 revolutions per minute. Controlling the frequency is only one part of controlling a generator. Another part is controlling the voltage. There are actually 3 factors that determine the voltage output of any generator. First, there's the number of conductors. Second, there's the speed at which the generator rotor moves. And third, there's the strength of the field. Now, we just said that you adjust rotor speed to determine frequency. So, using that factor to adjust voltage, too, isn't going to work. Besides, we want our generators to operate at a constant frequency. The number of conductors, or windings, a generator has is determined by its design. So adjusting that factor isn't possible either. The only thing left is to adjust the strength of the field. You can do this by changing the amount of current that flows through the electromagnet. So far, we've only been talking about single-phase generators, since all generators operate on the same basic principle. They use a magnetic field, a conductor, and relative motion to produce a voltage. However, the generators in your plant are almost certainly three-phase generators. Instead of one conductor or winding, there are three. This means that you get three output voltages. Instead of one sine wave for each revolution of the rotor, there are three. The three windings are spaced exactly 120 degrees apart on the armature. So the sine waves occur at three different intervals, or phases. Everything occurs at three different times during one revolution of the rotor. Three-phase generators are used because they can produce more power than single-phase generators. The transmission lines that leave your plant carry three-phase power so that more power can be transmitted. And the larger, more powerful motors in the plant operate on three-phase voltage. We're going to look at motors later on, and you'll see what I mean. For now, why don't you read through the material in your text that applies to what we've just covered on how an AC generator works and how you can adjust the voltage and frequency. Make sure it's all clear to you. We're going to be talking about DC generators next, and you'll need this information because AC generators and DC generators have a lot in common. If you have any questions that aren't cleared up after you've read the text, be sure to ask your instructor about them. Well, we know how AC generators operate. Now let's talk about DC generators. Like an AC generator, a DC generator converts mechanical energy into electrical energy. DC generators perform many useful functions around the plant, like exciters, for instance. An exciter is a DC generator used to supply power to the field of an AC generator. It provides current, or excitation, for the main generator, and that's how it gets its name. Another way a DC generator can be used is to charge batteries. You know how important that is. Well, in this segment, we're going to look at how a DC generator is constructed, how each part functions, and exactly how it generates a DC voltage. Then we'll talk about ripple. Ripple is another term for the fluctuation in the voltage output you get from a DC generator. We'll see how it can be minimized. Okay, let's get started. DC generators look a lot like AC generators, so don't be surprised if some of this seems familiar. This DC generator looks almost exactly like the simple AC generator we saw earlier. The only difference is that it has a commutator instead of slip rings. As we'll see, the commutator is the part that changes AC to DC. This DC generator operates like the simple AC generator too. As the loop rotates, it cuts through the flux lines of the magnetic field. This action induces an AC voltage in the loop. The voltage remains an AC voltage until it reaches the commutator. Then, the AC voltage is converted to DC by the commutator. Knowing exactly how the commutator is built and how it interacts with the brushes is the key to understanding how this generator works. So let's look at the commutator and the brushes a little more closely. Now this commutator is made in two segments, half-cylinder pieces of smooth conducting material. The two segments are separated by insulating material. Each segment of the commutator is permanently connected to one end of the loop, so the commutator rotates as the loop rotates. The two brushes are made of soft conducting material, such as carbon. They're stationary. The commutator slides against the brushes as the loop turns. This means that each brush is in contact with both ends of the loop, one after another. Now that we've seen how the commutator moves in relation to the brushes, let's see if we can work out exactly how this generator produces a DC output. As the conductor rotates from 0 degrees to 90 degrees, the induced voltage increases to a maximum value. As rotation continues, the voltage decreases to a minimum value at 180 degrees. From 180 degrees to 270 degrees, the induced voltage builds up to its peak negative value. And finally, from 270 degrees to 360 degrees, it decreases again to its minimum value. Sounds familiar, doesn't it? Well, so far it's just like an AC generator. In an AC generator, the slip rings transmit the AC voltage directly to the brushes. Each slip ring is connected to one end of the loop. When its end of the loop is in the positive portion of the cycle, the slip ring transmits positive voltage. When its end of the loop is in the negative portion of the cycle, that slip ring transmits negative voltage. Each brush gets both positive and negative voltage. The relationship between the commutator and its brushes is a bit different. Watch closely and you'll see what I mean. The left-hand brush is always in contact with the commutator segment attached to the side of the loop that is moving upward. The left-hand brush is always negative, and the right-hand brush is always in contact with the commutator segment attached to the side of the loop that is moving downward. The right-hand brush is always positive. By the way, did you notice that as the commutator segments passed from one brush to the other, there was a point where each segment contacted both brushes? It happens twice in each revolution, at 360 degrees and at 180 degrees. Well, these 2 points are the points where no voltage is induced, so this position is called the neutral plane. This is how it appears on the sine wave. It's a good thing that there's no voltage induced, because at this point, the brushes are shorting the ends of the loop. If the voltage weren't zero, there'd be an awful lot of current flowing through the loop, enough to seriously damage the generator. But on the other hand, the relationship between the commutator and the brushes means that the DC voltage output reaches its peak and falls to zero twice during each full rotation of the loop. This variation in the output voltage is called ripple, and it makes DC voltage unsuitable for many applications. Ripple also lowers the effective value of the output voltage to about 50% of its peak value. Now, ripple isn't something you absolutely have to live with. Our model of a DC generator is a very simple one. We've been using it just to give you a basic idea of how a DC generator operates. If we modify it a little by adding another rotating loop at right angles to this one, we can reduce the effect of the ripple. And by reducing the ripple, we also raise the average value of the generator's output. Now we've got 2 loops. The ends of each loop are connected to separate commutator segments, so now we have 4 commutator segments. We didn't add any more brushes. We still have only 2, and they're in the same places as before. For each loop, the brushes and the commutator segments work just the same way they did in the single loop generator. As the loops and the commutator segments rotate, the brushes make contact with each segment in turn. Again, one brush is always in contact with the ends of the loops that are negative, and the other brush is always in contact with the ends that are positive. As the loops rotate, one loop is always 90 degrees behind the other. So when the voltage coming off one loop is decreasing, the voltage coming off the other loop is increasing. And the brushes are always in contact with the segments of the loop that have the greatest induced voltage. As the voltage in one loop drops below the voltage in the other loop, the brushes pass from the commutator segments of the loop with the decreasing voltage to the segments of the loop with the increasing voltage. This is called switching, and it occurs 4 times during each full rotation of the 2 loops. Switching always occurs when voltage in the 2 loops are equal. With equal voltages, there's no current flow during switching. Because of this switching, the generator output voltage never falls below about 70% of the peak voltage induced in either loop. 70% is better than the 50% we had with a single loop, isn't it? Okay, so our modification works. Using 2 separate loops did decrease the ripple in the output voltage. It didn't have any effect on the peak output voltage. That stayed the same. But the average output is higher, as you can see on the graph. If we could add more and more loops and reduce the ripple even more, then the output voltage would become very nearly steady DC. Remember, though, that for every separate loop we add, we have to add 2 more commutator segments, too, one for each end of the loop. Real DC generators have many loops and many commutator segments. Well, that just about covers the basics of DC generators. You've seen how a simple DC generator works and how it can be modified to take care of output fluctuations. Why don't you take some time now to read over this material in your text? The next thing we're going to talk about is motors. Motors are sort of like generators in reverse. So before we start talking about motors, be sure everything we've said about generators is clear to you. If it's not, ask your instructor. Electric motors, whether they're AC or DC, play almost as important a part in the plant as generators. Large or small, they keep things moving by converting electrical energy into mechanical energy. We're going to be looking at both types of motors, AC and DC. We'll start with the basic facts about how a motor works, and then we'll see exactly how AC motors differ from DC motors. Most of the basic facts about motors will be familiar to you because motor action, what makes motors turn, is based on something you're already familiar with, magnetic force. It is the interaction between 2 magnetic fields that actually causes motors to rotate. Now, as you know, magnetic force is invisible, but we can see the effects of the force. They show up best when I try to put the poles of these magnets close together. Here we have north, here we have south. When they are put north to north, they repel each other. And now we're going to have north to south, and we find that opposites attract each other. You'll find that in most motors, the magnetic fields are created by a current-carrying conductor. But here, to keep it simple, we'll use 1 permanent magnet and 1 current-carrying conductor. This is how a basic DC motor is built. This permanent magnet provides one of the magnetic fields. The magnetic flux lines leave the north pole of the magnet, cross the gap, and enter the south pole. In the middle of this field is the current-carrying conductor, a loop of wire. Each end of the loop is connected to 1 segment of a commutator, which rotates with the loop. The commutator segments slide against the brushes, which supply DC power to the loop. The loop is both the rotor and the armature in this motor. Remember, the rotor is the part that turns, and the armature is the part that carries most of the current. Looks familiar, doesn't it? Well, it should. It's just like the DC generator we saw in the last segment. That's because the functions of a DC motor and a DC generator are interchangeable. A generator can be operated as a motor and vice versa. The difference between a DC generator and a DC motor isn't in how they're built. It's in how they move. In a generator, the loop is turned by a motor or a turbine, and current leaves the loop. In a motor, current is supplied to the loop to make it turn. You can see what I mean here. When voltage is applied to the loop, current flows through it. Now remember when we said that current flowing in a conductor produces a magnetic field? Well, that's exactly what happens in the loop of this motor. A magnetic field is produced with a north pole and a south pole perpendicular to the loop. This is our second magnetic field. The north pole of the permanent magnet attracts the south pole of the loop. And the south pole of the permanent magnet attracts the north pole of the loop. The force of this attraction is what turns the loop. At the point where the north pole of the permanent magnet and the south pole of the loop are exactly opposite, the motion stops, unless something changes. But at this instant, the commutator reverses the current in the loop. Thus, the north and south poles of the loop are reversed, and the motion continues. Now, you know what happens when two like poles of a magnet come together. In this case, the loop is repelled, so it continues to turn. The loop will keep on turning as long as the two magnetic fields interact this way. Now, when you look at a DC motor in the plant, you may see a lot of commutator segments. From what we covered about DC generators, you know that more commutator segments mean more power, and that power is a lot more uniform too. But the DC motors in your plant all work on the same principles that this simple one does. Well, that covers the basic facts about DC motors. Now let's go to AC motors. You'll find a lot more AC motors around because they're more efficient than DC motors. DC motors are more commonly used for emergency applications in the plant. There are several different types of AC motors. We're going to look at a couple of them. We'll check out a single-phase AC motor first. This type is usually a small motor. Then we'll look at a three-phase motor. Three-phase motors are larger, as a rule, and they can produce a larger turning force. Okay, now on this single-phase motor, we have a permanent magnet for a rotor. These wires or windings around the stator make it an electromagnet. What we want to see really is the interaction between the rotor and the stator, the two magnetic fields. We can show the effects of this interaction here in the form of a sine wave. We've divided the sine wave into 5 sections: A, B, C, D, and E. Now we're going to apply alternating current to the stator. When we first apply it to the winding at A, there's zero current, so no field is developed between the stator poles. Now, in the time between A and B, the magnetic field builds up as the applied current does. The stator starts developing magnetic poles. Since like poles repel, the rotor is first repelled by the magnetic field, so it starts to turn. Then, since opposite poles attract, the rotor continues to rotate until its poles come under the opposite poles of the stator. Between B and C, the magnetic field decreases because the current decreases. At C, current is zero and there's no magnetic field. The rotor's now in line with the stator. With no current, inertia keeps the rotor moving until the magnetic field builds up again. Inertia, in this case, is the tendency of a moving object to keep moving. It's what allows the motor action to continue. In the time between C and D, the magnetic field builds up again in the stator as the current increases. But you can see from the poles that the magnetic field has reversed because the direction of current flow reversed. The north pole is here and the south pole is here. Since like poles repel, the rotor's repelled again, so it keeps turning. At D, the rotor continues to turn because opposite poles attract. Between D and E, the magnetic field's decreasing again because the current's decreasing. The motor action just described continues as long as alternating current is applied. Now, this type of single-phase motor has a fancy name. It's called a synchronous motor. That's another way of saying that the rotor's turning speed is the same as the speed at which the stator's magnetic field alternates. The next type of single-phase motor we're going to look at is called an induction motor. In an induction motor, there is an induced current flowing in the rotor, so the rotor is an electromagnet. The rotor follows the alternation of the stator's magnetic field. Well, let's see how an induction motor works. These two coils are connected to an AC power supply. They provide the stator's magnetic field. And this aluminum plate is the rotor. Now, when I position the aluminum plate over the coils, there's a voltage induced in the plate. The voltage causes a current to flow, and that current makes the aluminum plate rotor an electromagnet. And as the electromagnet's field interacts with the magnetic field of the two coils, the aluminum plate turns. Now, we'll be looking at motors again in the next segment, but instead of single-phase voltage, we'll see how they work with a three-phase voltage. Before we go on, stop and review this section in your text. If you have any questions on motors in general or single-phase motors in particular, be sure to clear them up with your instructor. You know how motors work now, DC motors and single-phase AC motors. But because the motors we've been looking at are such simple ones, not nearly as complex as the motors in your plant, you've really been learning theory instead of practical application. You see, with only one winding or conductor, a motor doesn't have much turning force. Most of the motors you'll be dealing with in the plant are heavy-duty equipment. They have to have a lot more turning force to do the jobs they do. So most of them are three-phase motors. They have three windings, which means that they have 3 times as much turning force as any of the motors we've seen so far. We're going to connect this three-phase motor to the three-phase generator we saw earlier. Then we'll be able to see exactly how the generator supplies power to the motor. Now, the A winding of the generator is connected to the A winding of the motor. The same is true for the B and C windings. The rotors in both the motor and the generator are electromagnets. Remember how a generator works? You know the rotor must be turning to generate voltage. The mechanical force to turn the rotor can be provided by a turbine, a motor, or even falling water. It doesn't much matter as long as the rotor turns. So, here we have the 3 things necessary to induce a voltage: a magnetic field from the electromagnet on the rotor, relative motion from the turning rotor, and a conductor, which is the windings on the stator. As the rotor on the generator turns, a voltage is induced in the stator windings. Every time the rotor on the generator passes the A winding, voltage is induced in that winding. The voltage in the A winding on the generator causes current to flow to the A winding on the motor. Current flowing through the A winding on the motor builds up a magnetic field around that winding. The rotor on the motor aligns itself with the A winding because of the magnetic attraction. As the generator's rotor continues to turn, the magnetic field and the motion induce a voltage in the B winding. So current flows through the B winding of the motor, and a magnetic field builds up around the B winding. The rotor on the motor then turns to align itself with the B winding. The same process is repeated as the generator's rotor reaches the C winding. A voltage is induced in the C winding. Current flows to the motor's C winding. A magnetic field is built up, and the motor's rotor turns to align itself with the C winding. As the process continues, the motor keeps turning. The motor keeps operating as long as the generator keeps producing voltage. This motor is a synchronous motor. The rotor travels at the same speed as the rotating magnetic field. As we saw earlier, an induction motor is different. In an induction motor, the rotor travels slower than the rotating magnetic field. The difference between the rotor speed and the speed of the magnetic field is called slip. In most induction motors, slip is 2 to 10%. Now, let's see why this is so. We've already seen how the magnetic field rotates, so we'll look at how an induction motor is constructed, and then we'll concentrate on how the rotor turns. The simplest and most widely used rotor for induction motors is the squirrel cage rotor. It has an iron core with copper bars or some other conductor running along it lengthwise. At each end of the rotor, there's a shorting ring that connects all the copper bars. As we apply voltage, we can see how the squirrel cage rotor turns. the stator of an induction motor becomes a rotating magnetic field, just like the one in the synchronous motor. As the stator field begins to rotate, its flux lines cut the copper bars around the surface of the squirrel cage rotor. The field induces a voltage in the bars. Because these copper bars are short circuits with low resistance, there's high current circulating in them. The high current produces a strong magnetic field. The magnetic field of the rotor is attracted to the rotating magnetic field of the stator, so the rotor turns with the stator field. Okay, that's how the rotor turns. You might think that its speed would build to equal the speed of the rotating magnetic field eventually. But if the rotor turns at exactly the same speed as the stator's magnetic field, there's no relative difference in motion between the field and the rotor. With no difference, the copper bars in the rotor don't cut the field's flux lines, and there isn't any current induced in the rotor. Without induction, the rotor loses its magnetic field, and it isn't attracted to the stator's magnetic field. So, the rotor slips behind. The field now cuts through the rotor, inducing voltage and once again producing a strong magnetic field. Without slip, an induction motor won't turn. Well, that's how a basic three-phase AC induction motor works. We've covered a lot of information in this unit. We started with batteries, and then we went on to cover AC and DC generators, DC motors, and single-phase and three-phase AC motors. When you review all this material in your text, make sure you understand it. Then you can go out into the plant and see the equipment in action.